Hello, welcome to this short tutorial which reviews how to test goodness of fit between observed and expected frequencies using R. Now, if deviations between observed counts and expected counts arise by chance alone, then a certain statistic, which is this one, it's the sum of the deviations between observed and expected squared divided by expected, summed over all individual classes, will follow a chi-squared distribution with the number of classes minus 1 degrees of freedom. Well, that's the theory. Let's see how it actually applies in practice. Here's a particular example which comes from Fowler and Cohen, Practical Statistics for Field Biology, and it deals with the distribution of midge pupae in a sample. In this sample, there were 24 Dixella automalis midge pupae, 32 aestivalis, 10 amphibia, and 9 attica, with a total of 75 midge pupae counted altogether. The main question here is whether these data could be considered to have been sampled from a population in which each of these species is equally represented, i.e. the underlying frequencies are homogeneous. How do we test for this? Well, the expected frequencies of these midge pupae species, if indeed they were homogeneously distributed, i.e. they were all equal proportions, is that total number of observations divided by 4, i.e. 18.75 in each of these cases. So here we have our observations, and here we have the expectations following the hypothesis of homogeneity of frequencies. It doesn't matter at all that the expectations is fractional. This just arises out of dividing this number 75 by 4. How do we compute the test statistic which we compare with the chi-squared? Well, here it is. For each of the observations and expectations, we work out the difference between observed and expected. We square it and divide by the expected, which is 18.75 in each cases. When we sum for each of the 4 classes, then we get a value of 19.99, which we can then compare with a classical chi-squared distribution for the number of classes minus 1, which is 3 degrees of freedom. Now, if the theory which generated the expectations, in this case the homogeneous frequencies, were true, then the differences between observed and expecteds should, when calculated in this way, follow a chi-squared distribution if the null hypothesis was true. So we can compare our computed test statistic with a chi-squared to see whether we can reject that null hypothesis or not. Let's have a look at how that's done in R. Here are our observed frequencies, 24, 32, 10 and 9. And it really couldn't be simpler. In R we simply say chi-squared test, and the default is a test for homogeneous distribution of underlying frequencies. These are our observations of the sample. So the default is homogeneous frequencies, so we simply put chi-squared test observed frequencies, and we are then given the test statistic, which is 19.99, the degrees of freedom, and the probability of obtaining that test statistic or a more extreme if the null hypothesis was true. It's really very small, so we reject the null hypothesis in this case. How would we conduct a test if our underlying model which generated the expected frequencies wasn't one of homogeneous frequencies, but maybe emphasized some groups over others. Let's say, for example, we felt that the right model is one of 40% in each of the first two species and 10% in the latter two species. In this case, we could conduct a test on the observed frequencies, but here, instead of adopting the default, we could say 0.4, 0.4, 0.1 and 0.1. You'll note that these relative frequencies always add up to 1. Now, after conducting this test, we can see that the chi-squared value is that much smaller. It's 2.4667. We've got 3 degrees of freedom. And in this case, when tested against this null hypothesis here, generating the expecteds, we cannot reject that null hypothesis. So we cannot, in that particular case, reject the null hypothesis that the frequencies of observed follow from the underlying expected distribution of 40%, 40%, 10%, and 10%. Now let's move on to look at another application of goodness of fit statistics. This is a well-known application that some of you may have seen already. It with regards a formal test of association between one form of classification, like leaf type, and another form of classification, like soil type, all based on counts of individuals with these combinations of attributes. This particular example comes from Sokal and Rolf's biometry, and it deals with tree types. Either they've got hairy leaves or smooth leaves in mineral-rich or non-mineral-rich soils. There were a total of 100 trees surveyed, and you'll see that 34 of them were found in serpentine soils, and 66 were found in non-mineral rich or non-serpentine soils, whereas 72 of the trees had smooth leaves and 28 of the trees had hairy leaves. So you'll see that for each individual observation we could classify both the type of tree with regard to its leaf type and where it was growing with regard to the type of soil. Incidentally, this way of showing the frequencies of different combinations of outcomes is known as a contingency table. Here are our observations, and let's have a look at what the expectations are. I'm putting them here in red underneath the observations. How do we calculate these expectations? Well, I'll take you through a single example for this 9.52 so we can see how the expectations are derived. You'll note that the expectations assume that the form of leaf type classification is entirely independent of the soil type classification. So let's have a look how it's done. The probability of being a hairy leaf tree is 28 upon 100 because it's that column total divided by the overall total. The probability of the tree being in serpentine soils, in this case, is 34 divided by 100 because here there are 34 trees in the mineral-rich soils. What's the probability of both being hairy and serpentine? Well, if they are independent forms of classification, then the probability of this and this arising is 28 upon 100 times 34 by 100. Now, that's the overall probability of hairy and serpentine, assuming they're independent. What about the frequency? Well, we need to work out this probability times 100 to give us our expected frequency. And what we'll see here is that each of these expected values can be derived simply by multiplying the row total by the column total divided by the overall total, and that will give us each of these different values here for the expected, assuming that the types of classification are entirely independent of one another. Well, how can we test for this independence? What we do here is we use a chi-squared test for goodness of fit to compare between our observations and our expectations, assuming independence of classification. So here is our table. Here's how we would do it by hand. For each of the classes, and there are 4 of them, we would work out the difference between the observed and the expected value. We would square it and divide by its expected value for each of those 4. Now in this particular case, data is used more than once, in that observations here are used to calculate this total as well as observations here. Given this interdependence, it turns out that the appropriate number of degrees of freedom with which this test statistic is compared is actually the number of rows minus 1 times the number of columns minus 1, which in this case is 1 degree of freedom. How can we conduct this test in R? Well, the first thing we do is we put our data into a vector called observed frequency in this case. We can then turn that vector into a matrix. It's a 2 by 2 matrix with 2 rows and 2 columns. We're filling it by rows and there's 2 columns. Then we can perform a chi-squared test on that matrix called observed. In this case, I've gone without a technical adjustment to the calculation of chi-squared, and that is known as the Yates continuity correction. How would we look back at the expected frequencies which have helped to generate this Pearson statistic of about 1.36? Well, we simply go $sign expected, and here we can rescue those very same expected frequencies. Just one more important point to note, although it doesn't necessarily apply very well here. We have to be particularly cautious of interpreting goodness of fit tests based on the chi-squared distribution when our expected values tend to be small, in particular when they are less than 5. What do we do in these cases? Well, it depends on your design, but one good solution which applies to many forms of design is to fit what they call a Fisher's exact test. How would we fit a Fisher's exact test in this particular case? Well, our matrix is called observed. We simply say Fisher.test. And what we are given here is an exact p-value according to the Fisher test. No chi-squared value is computed or any test statistic compared with the chi-squared. Instead, we get an exact value for that significance. The test assumes that the row and column totals are controlled, and when one or both are not controlled by the experimenter, then Fisher's exact test is not really considered exact. Thank you for listening to this R Labs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.